Well, let us continue. And our next speaker, and the last speaker for today, is Professor Nikolai Krylov, the most Western speaker of our conference. Please, Nikolai Vladimirovich.
Oh, thank you. I am very honored to get invited to this conference, and I was of a very high opinion of Seva Salonnikov, always as a mathematician, as a person, very warm person, and I wish him many returns. By the way, is the sound high enough?
Okay.
Okay. So I will be speaking about the subject which I started to work on 2.5 years ago. You know, when you are about 80, it's a good time to start something new. This was a suggestion by Henry Dong. I was working on a problem, and he actually told me that more spaces could be very helpful in these questions. Before, I was thinking that more spaces are used to the following, that you have the right hand side of the equation slightly better than in LP, and then you get much better properties of the derivatives. And this is not my my goal to get better properties of derivatives, but it turned out that actually more spaces are very helpful in studying equations with when the coefficients are, say, drift has very bad singularities, and I was very much surprised that more spaces are instrumental in this regard. Also, to my big surprise, I found that the theory of more spaces is in connection to the partial differential equation is underdeveloped, very underdeveloped. Just there are books, say, and 2 books which are the title is more spaces and partial differential equations, and say simplest questions which arise in the theory of partial differential are left out. So anyway, let's get closer to the subject. So I will be talking about parabolic equations in more spaces. So this coefficient will be in almost in VMO, actually VMO in X and no measurable in time. And Mori, B and C. There is no C here, but on the next slide you will see. So these are usual notation, and this is the equation we are going to study. Minus C plus lambda, and lambda will be sufficiently large. So we are interested in rather regular solutions, and B and C and F with rather poor integrability properties. And the main motivation for me was to get the necessary tools to show that the corresponding eta stochastic equations admit solutions for larger than previously known class of B. C was not important. There is eta in eta stochastic equation. There is only say A or square root of A and B. In Ryokin and Zhao 2020, such program was realized when A is the unit matrix, which is important because in very many papers, actually, A is a unit matrix. And in the basic case, B satisfies this integrability condition, which is called Ladыжинskaya Prodi-Serine condition. So I write a very insightful observation in the bullet of 6, and this is on archive, 2023 actually. Is that for solutions of either stochastic equation to exist, in case of unit A, it suffices to have a number S and rho 0 bigger than 0, such that this holds. So what this is? CR is the cylinder with base being a ball of radius R, standard, so means that base of radius R and the height is R squared. And so for any standard cylinder and height in time, with respect to time. So that this thing would be less than a constant times R to the minus 1, and well, B is sufficiently small.
What happens?
Okay, so using Hölder's inequality, it's easily shown that if you take S, P minimum with P and Q, the left hand side, this one, will be less than the constant times the left hand side of of this one, just by Hölder's inequality. But with instead of R, here will be this cylinder actually, and this one with B times indicator of CR in place of B, and this one can be made as small as we like on the account of choosing rho 0 small enough, and not rho 0. Okay. So the goal of this talk is to combine, in a sense, 1, 2, and 1, 3, and develop the solvability theory of the equation in more classes of functions without applying them to each stochastic equation. The application was done in a separate paper. Here is an example in which the theory is applicable. So B is a constant, C is a different C, just a constant bigger than 0, is small enough, and H is this thing. There is also sigma, actually it's A, but that's okay. So this is a very discontinuous function. It is in VMO. This is known that this function is VMO, but very discontinuous anyway. And H has this singularity, x to the minus 1 and times something scale invariant. This example is inadmissible in Röpner and Zhao because B is too singular. But, if you compute the left-hand side of the condition in Röpner and Zhao, then it will be infinity. And but admissible in fixed and yields weak solutions of eta equations that are conditionally weakly unique. But then this has almost nothing to do with partial differential equations. Now some notation for P and Q in this one and domain. By LPQ, we mean the space of Borel functions with then on Q with the norm with one of the two ways. The norm is given in one of two ways, which is fixed throughout the top. Either you first integrate with respect to x, and P is always relative to x, and then integrate with respect to t, or first integrate with respect to t, and then integrate with respect to x. Again, x related to p and
Nikolai,
t.
one moment, please. I with index q. Это что, характеристическая функция? Я что не помню сразу.
Oh, yes, yes. Why? And then this is the indicator function of q.
Oh, okay.
Yeah, you may be surprised that this norm is useful, but exactly this norm is used to treat B from this example. Because if you take the usual norm, the usual order, it will be infinity. But in this order, it will be finite and can be made as small as we like, because they have the constant factor in front. So that actually this is also a useful norm.
Yura, I remind that in probability, characteristic function has different meanings.
Oh yes, yes. That yes, we called it indicator because the characteristic function in probability theory is absolutely different. The meaning has a different meaning. So LPQ, it's LPQ of RD plus 1 of the whole space. W1 to PQ, absolutely. No, absolutely normal thing when derivative in time and second derivative in x and third derivative in x, and u itself is an LPQ. And the norm is introduced in an obvious way. Again, I drop q if q is RD plus 1. This is the ball, standard notation, ball of radius r centered at x. And this is cylinder. So from t to t plus tau is in time, and this is tau, and this is rho, cylinder, ball of radius rho centered at x. C rho, adjust C rho squared rho. When the first argument is rho squared, then it's just 0. And bold C rho is the collection of C rho Tx. Now, this notation also usual the average of F over Z gamma. This is the volume of gamma. And I also use a notation very convenient. I don't know how to call it. Maybe it's a reduced norm. So you this is equal to this thing. So you actually divide the LPQ norm of F over C by the volume of C. But not by the volume of C, but by the norm of 1 in this space, so that the reduced norm of 1 will be 1. So this is what I call the reduced norm. Then I also need more spaces. The PQ is in 1 infinity, and beta is bigger or equal to 0. Actually, will be strictly bigger than 0 by simple reason. And this, my notation is different from all other people notation. And because I introduced the norm differently. If you put here different indices, you will get the standard notation of Morris space. So it is the same Morris space, but with indices which are organized in this way. And you will see that this is very natural and very useful notation. So you take the average norm or reduced norm of G in PQ over the cylinder. Cylinder is in C rho less than or equal to 1, and takes a sum over all cylinders. And then E1 to PQ beta is naturally this thing, and provide this with an obvious norm. We are going to use some properties of the spaces proved in 8. And 8 is a paper my paper which appeared in last year. Yeah. Unfortunately, funny enough, they were not known. Just even some of them were not known even when it's not a parabolic setting but elliptic setting. By the way, elliptic setting means that G is just independent of time, and this will be the norm will be. You can introduce the norm in the same way as if G depended on T. But if it's independent of T, it will be an elliptic version. Okay, then here is the here is the main result. Значит, PQ is in 1 infinity, beta 0 is in 0 infinity, but different from 1 and 2. And we fix P and Q such that D over P plus 2 over Q not less than or equal to 1, as in Ladyrensky product certain condition, but bigger or equal to beta 0. Bigger or equal, anyway. Beta could be less than 1, could be close to 0. So the setting is quite different. This we fix some rho A, which will be responsible for this condition on A. Rho BC, which are responsible for conditions on B and C. And when I say will be specified below, later, it will not be specified. It will be just required for them to be sufficiently small, and I will not describe what does it mean. So this is a condition on A. You take cylinder of radius less than or equal to rho A, which is fixed, subtract from ATX the average actually of ATX on the level T with respect to X. So this is the average. T is fixed, but you integrate with respect to dx ds over the C. So you actually average this quantity on the level T with respect to X and subtract, and then require this to be sufficiently small. So it's
I'm
not
sorry, what is DS? What is DS?
this.
Oh,
No,
this
well,
way.
points in the C are called SX. So dx ds, this is the element of volume in C. No, there is no S here. Okay, that's fine. Yeah. So it only means that actually ds is the extra variable, but then I have to specify what x is. I have to then say what C is. C is, let's say, some interval with respect to T and times B. Then actually this is the average of ATX over B. But it's also okay like that. Now assumption. Let's not pay to this case beta. The main case is beta bigger than 1, beta 0 bigger than 1, and less than 2. But anyway, what you have, you take your P and Q, which are fixed, then beta 0 such that this holds, and consider this space. P beta 0 is less than D. Because of this inequality, because of this condition on beta 0. You take the reduced norm of B in LPQ times R, and R is the radius of C. It takes sup over all R's less than this one. Let me show that this is an example. So B is 1 over X, 1 over absolute value of X is good enough. And this is a huge singularity in of the first order terms, just huge. The same when if beta 0 is bigger than 2, which is, as I said, is a not very important case. This is R squared here. And in this case, the example is, wait. The example is, say, 1 over x squared. Very singular coefficient of u. I'm saying let's specify theta. Let's not do it because it's. I refer to lemma 6.5, to which we will never come. But anyway, there is a way to specify theta, which will be depending on d, delta, alpha, and p and q. And now we consider this operator with c. And this is main result. there is a constant nu is defined in a certain way, also depending on our basic parameters. So under the above assumptions, there exist small B check and C check, and the big lambda zero, depending on this and that, such that if our conditions holds with B check and C check, then for lambda bigger than this times lambda zero check, this rho was the size of balls for which size of cylinders for which the conditions on B and C were imposed, and this rho doesn't enter this set of arguments here or here, and only in this way. But so that lambda is big enough. So then there exists a unique solution in this space of this equation. Unfortunately, actually, this should be deleted because it's written twice. Okay. Because then there was already C there, and then I subtract C, so there will be no C. Strange. Yes, so there is a unique solution, and this is so that the equation in the whole space. This is the space of functions given on the whole RD plus 1. And there is such an estimate. So that this is also a very useful notation when instead of writing separately normal this plus normal this plus normal this plus normal this, you just use a comma. And this I borrowed from Ладыжинская Уральцева books. Мы до Ладыжинска Салоник Уральцева book. Now, what are the, so you saw that B and C could be quite singular. What the solution? What are the properties of this solution? And P and Q could be small, because there is the condition is that D over P plus 2 over Q bigger than beta 0. Well, P and Q will be as close to 1 as you like. Then obviously this is in Sobolev class locally. Then if beta 0 is bigger than 1, there will be lemma for which says that du is in LRS locally. So R, you integrate with respect to X with power R and S. So the actual statement is that du is in this space. What is good about this notation? Look, your function is in E1, 2, beta 0, PQ, and this is RS beta 0 minus 1. And what is the connection between RS and PQ? Very simple. The product of this one times S is the same as beta 0 times Q. No, very simple. That's why I'm saying that my notation is very good. And the product of beta 0 minus 1 times R is the same as beta 0 times P. Nothing to memorize. Then the property. If beta 0 is less than two, then it turns out that U is bounded and Helder continuous. So again, P and Q are as small, as close to 1 as we like. But where 0 is less than 2, then it is bounded and Helder continuous. And if beta 0 is less than 1, then the gradient is bounded. And the coefficients are very singular. Now, it turns out that we checked, this is the bound for this bound on B should be generally small. To show this, we take D bigger than 4. I think bigger than 3, one can also give an example. By the way, in the whole on the top, dimension is bigger or equal to 3. So this is PQ, beta 0, P prime. It doesn't really matter what it is. What matters is their properties. So that beta 0 is bigger than 2, less than this property, and this holds. Then we take any lambda bigger than 0 and consider the function from Ladyrensky Solonic-Differential book. There is no lambda t there, and there is a sign minus, but my equation is different. I write derivative in time and plus Laplacian, no, not minus. And this equation. So this function is equal to this one if t is less than 0 and ut is 0 when t is bigger than 0. So this function satisfies this equation in the whole space, and t from minus infinity to infinity, and x in Rd. So equation in Rd plus 1. So what is easy to check then? V, which is one of those, belongs to L P prime, and P prime is less than this thing. And by Helder's inequality, then what happens that this quantity times rho to the B0 less than this one, which I said is finite. So in this sense, that U will actually belongs to one E1 to PQ beta 0. In addition, for B equal to this one, the absolute value will be D over absolute value of X. This quantity is finite and independent of rho BC. Because of this, what I said that 1 over absolute value of X is good enough. However, the estimate fails. This estimate, you see, F is 0, so this estimate fails because this is not 0 and this is 0. So which means that the factor D here is not sufficiently small. If you take D sufficiently small constant here, then the equation will be okay, so admitting nice solution in this space and nice and unique solution. But if B, so this shows that Morris spaces allow us to get almost sharp results in what concerns singular coefficients. Now, technical tools. So in the last 5 minutes, here is approximation result. F is in EPQ beta, and this one, beta 0, beta prime, is bigger. What is interesting, actually, pretty trivial, but interesting, that actually, if you take the modified function, subtract and take the norm, it could be that it is just bigger than the normal f. You subtract, no. Yes, sorry, this is not beta prime. This is beta. So that in the same space, modification doesn't do any good. Then a very surprising story here. As I said, that there are books about Morris spaces, but no such inequality is there. Can you imagine that? That you want to apply your theory to partial differential equation. You need to be able to estimate the first derivative through constant epsilon times second order derivatives plus 1 over epsilon times u. This inequality belongs to me. Can you imagine that? As far as I know, I couldn't find it anywhere. What I saw in 2017, the first attempt to prove this inequality, and this was false, just plain false. Why? Because this attempt was based on this inequality without R here. But without R here, this is trivially false, because if you divide by the volume of B of the R and let volume go to 0, you'll have pointwise estimate first derivative through the second derivative of function itself, if there is no R. But there is R, and then how do you prove this? You multiply this thing by R to the beta, good enough here and here. But here, R to the beta minus 1, and not R to the beta. So how to prove this? That's what I said. It's not a big trick, but still, in 2017, I saw the first attempt to prove it, and it was wrong. Then embedding. Embedding beta less than 2, then it turns out that the function is bounded and continuous, and here is the estimate. And the last embedding, which is actually in the elliptic case, it was known, and it is so-called Adams theorem. But in parabolic case, it's I proved it. And what is again interesting, the relation between how to memorize this embedding theorem. That the product of S times beta minus 1, S times beta minus 1 is the same as Q times beta. Very convenient. And if beta bigger than 1, if beta bigger than 2, then you can estimate U with the beta minus 2, but the rule is the same. The product of this one is the same as P Q times beta. Okay, as I see my time is up. Again, thank you very much for inviting me. And I again wish many happy returns. Thank you.
Okay. Questions or comments, please? Так, Тим. Do you have a question?
У вас там, по-моему,
Окей,
коэффициенты
yes,
были
yes,
типа
sorry.
БМУ или ВМУ, я не помню уже. БМУ или ВМУ? На старший коэффициент уравнения.
ВМО?
ВМУ, да? Все, спасибо.
Да,
Так.
главный коэффициент VMO, main coefficient in VMO.
Так, Тим.
No, but
Okay.
not exactly. I don't know how far it is from VMO, by the way, because I only require this the oscillation to be small enough, and that's it.
Я понял, хорошо.
Yeah, okay. Тим.
Okay, I would like to ask the question. Do you think that if you impose the sign condition on the divergence of the drift term in such a way that this drift term formally provides a positive support to the quadratic form of the elliptic operator formally, then you can actually eliminate smallness condition on the Mori norm of the drift. Because in all counterexamples you showed, as far as I understand, the divergence has the wrong sign. It destroys the quadratic form of the elliptic operator.
Could be, but
In Lebesgue spaces, this is the case.
Then you have to assume that divergence exists. So, well,
No, divergence is
distributional.
in distribution.
I understand. But still, it's something related to the derivatives, and I want to avoid. I don't know the answer to this question. It could be.
Yeah, I think this is the case because in Lebesgue spaces this is the case. So we can imagine that here it is the case too.
And one more, probably not question, but just a comment.
By the way, but I doubt that this will help if A is only in VMO.
I see. Yes. This is.
Then you have to.
Okay.
Then you have to assume divergence form of the part. Well, in that's quite far from my interest. And that's no actually. So I'm sorry, I interrupted somebody.
And one more comment concerning the modification in Mori type spaces, which you mentioned. As you mentioned, a modification actually destroys the Mori norm, and you cannot control the Mori norm of modified function by the Mori norm of the original function for arbitrary Mori exponents.
No. You can control the norm of modified function is less than or equal than the norm of just Minkowski's inequality, nothing. But the modified function is not close to the function which is modified.
No, I don't believe, but because by modifying the local norm of a small integral, you have to increase by epsilon the size of the ball. And then when you divide back by radius, then your norm is and take supremum over all radius, then you obtain radius plus epsilon divided by radius, and it's blow us up for positive epsilon. So
no. You know, it does matter which norm you consider. Does matter, Mori norm or whatever norm. The norm of modified function is always less than the norm of the function which is modified. by Minkowski inequality, because modified function is the sum of shifted function.
Over bigger area. Okay.
No. What?
Okay, dear colleagues, okay, I think this is
Yeah, this is
the question for written discussion. Yeah, it is difficult.
But what is interesting? You take 1 over absolute value of x and cut it. And subtract a constant, so that to cut it on certain level. You know that the norm will not change of the cutoff function, because the supremum is attained on small radiuses. So as long as the height of this difference is the same, the norm is the same. It's simple and amazing, by the way. Very disturbing fact.
Окей, так, Михаил Васильевич, please.
Very quick question. Is this text available somewhere on archive, or otherwise? I could ask, of course, directly, but I don't want to benefit from personal communications, just to have same access for everyone.
Yes, yes, it is on archive.
Okay, Jose Francisco, please. Moment.
Yes, I apologize. Now you hear me. It was a quite interesting and novelty topic for me. My question is not technical, it's more kind of philosophical one. I'm wondering what was the motivation, and if you know any important new case where these estimates on parabolic equation on moral space, I mean, this regularity theory in moral space can be really important and can cover cases that the classical sub-level spaces usually cover. So what do you say about this need to go to these moral spaces?
As I said in the beginning of my talk, that my main motivation is stochastic equations. So that
yeah,
when the drift is bad, how bad would be the drift, so that we would have solutions, at least even in a weak sense, or also in a strong sense, solutions. So, and this enlarges the area of bad coefficients immensely.
Oh, I see. So for the stochastic equations, this is really a breakthrough, a step forward, important step.
Yes, step forward, yes. Yeah.
Thank you. I missed that at the beginning, sorry.
Easy to miss.
А мне понравился пример, когда в главной части опять Лапласа и массы члена. Но пусть классика будет. И там тоже пример был новый, уравнение, Z был новый. Вот мне понравилось. Я люблю классику.
Okay. Let's thank the speaker again.
Thank you very much. Thank you. It was a pleasure.
Please